All right, let's jump right in. Now, I know what you're thinking when you see a title like this one, the History Dependent Nominal Mu Calculus. It is a mouthful. It sounds incredibly academic and, let's be honest, a little intimidating. But what if I told you that by pulling apart this name piece by piece, we can actually unlock a really powerful way to understand and even prove that the complex software running our world is safe? Well, that's exactly what we're about to do. So there it is, in all its glory. The history-dependent nominal mu calculus. It's a type of what's called temporal logic, which is just a fancy way of saying it's a language for reasoning about things that happen over time. You can think of it as a kind of super logic, one that's built by smashing together three other powerful ideas, with each one solving a very specific problem. So here's our game plan. We're going to deconstruct this thing. First, we'll look at its core engine, the mu calculus. Then, we'll see how to add the ability to pinpoint specific moments in time using something called nominals. After that, we'll give our logic a memory, making it history-dependent. And then finally, we'll put all those pieces back together and talk about why any of this actually matters in the real world. Okay, first up, the mu calculus. This is our foundation. It's the engine that drives the whole thing. And if you're going to remember one thing about it, it's this. It's all about loops, repetition, and recursion. So the mu calculus is what's known as a modal logic, which is a logic of possibility, what could happen versus what must happen. But it has this special extension, these things called fixed point operators, mu and nu. You can think of mu as being for things that must eventually happen, like a program successfully finishing its job, and nu is for things that must always be true, like a critical system never ever crashing. It's these operators that make it so incredibly good at describing repeating behaviors. This quote, it absolutely nails it. The mu calculus is often called the assembly language for other temporal logics. And that's a perfect analogy. You know how assembly is the super low-level fundamental language that more complex programming languages are built on top of? Well, the mu calculus is like that for logic. It provides the absolute core building blocks for reasoning about how systems behave over time. And this has huge real-world consequences. With the mu calculus, we can formally prove with mathematical certainty that the systems we rely on are correct. For example, we can prove that a car's airbag system will always be ready to go, or that a bank transfer will eventually complete. This isn't just testing. It's about achieving mathematical proof that things work the way they're supposed to. Okay, so we have an engine that understands recursion. That's great, but what if we need to talk about a very specific moment in a system's life, a single point in time? Well, for that, we need a way to give those moments a name. And that is exactly what nominals do. A nominal is basically a special label that is true at one and only one unique state in the entire system. It's like putting a pin on a map. You're pointing to a very specific location, or in our case, a specific moment, and giving it a unique name like I or J. Now you can say, right now, we are at state I. So once you've named a state, let's call it I, you get this cool new power. You can use what's called a satisfaction operator, which looks like at I, to basically jump to that exact state and ask questions about it. You can say, is this property true back at that moment we named I? It's incredibly precise. And when you combine this naming ability with modal logic, you get what's called a hybrid logic. So what happens when we combine our powerful recursive engine, the mu calculus, with this new hyper-precise ability to name states? Well, you get the hybrid mu calculus. Now we can't just talk about repeating behaviors. We can talk about specific named moments within those repeating behaviors. It's a massive leap in how much detail we can describe. But we're still missing one final crucial piece of the puzzle. Most logics, including everything we've talked about so far, kind of have amnesia. They only care about right now and what might happen in the future. But what if the past matters? What if how you got here is important? To handle that, we need to introduce the logic of memory. And this slide really shows the difference. On the left, you have your standard memoryless logic. The truth of anything only depends on where you are now and where you can go. The past is forgotten. But on the right, you have a memoryful logic. Here, whether a statement is true can depend on the entire path, the whole history of states that led you to this moment. The past is no longer ignored. So how do you actually build this memory into a logic? Well, there are two main ways to do it. The first is to just add new tools, past operators, that let you explicitly look backward in time, to ask about the previous state, for example.
The second way, which is even more fundamental, is to change the very rules of the logic so that every single formula is automatically checked against the entire history of the computation.
Okay, we have all our pieces. We have the recursive engine, we have the state naming system, and we have a memory. Now let's assemble them into our final superlogic.
This table sums it up perfectly. The mu calculus gives us the power of recursion, so we can define repeating properties. The nominals give us the power of naming, so we can refer back to specific individual states. And history dependence gives us the power of memory, so we can reason about things that happened in the past. It's the combination of all three of these that makes this logic so incredibly expressive.
But, and this is a really big but, with great power comes great complexity. As this chart shows, the more expressive power you pack into a logic, the harder it becomes to analyze. In fact, for some of these super expressive logics, figuring out if a formula is even possible becomes undecidable. That means there's no computer program you can write that is guaranteed to always give you a simple yes or no answer. It's a fundamental trade-off that logicians and computer scientists are always wrestling with. So after all that, you might be wondering, why do we need something so ridiculously complex? The answer has everything to do with the complexity of the technology that we build and depend on every single day. The whole point of this is to create a single, unified language that can accurately describe the behavior of really complex systems where lots of things are happening at once. We need to be able to talk about timing, specific moments, repeating patterns, and the history of events, all at the same time, because in the real world, all those things are tangled together. Ultimately, it really boils down to one word: trust. The goal is to build a formal language that is powerful enough to mathematically prove that our most critical technology, from self-driving cars to medical implants, is not just reliable, but genuinely trustworthy. You know, as our technology gets more and more complex, this question of how we prove it's safe becomes more and more urgent. The answer probably isn't going to be simple, but it will almost certainly involve powerful tools and ideas just like the history-dependent nominal mu calculus.